Hey everyone, and welcome. Today, we are going to pull back the curtain on the DC motor. It's one of those amazing little engines that's kind of the unsung hero of our modern world. Seriously, they're in everything from your electric toothbrush to massive industrial machines. And today, we're going to break down exactly how they work.
So let me ask you a question. What do you think your kid's remote control car, that power drill in your garage, and a giant electric train all have in common? Yep, you guessed it. The answer is the spinning, rotational power of a DC motor. This simple-looking device is the magic that connects the world of electricity to the world of physical motion.
So, at its very core, a DC motor is basically a magician. It takes the invisible power of electricity, from a battery or a power source, and poof! It transforms it into the very real, very physical force of motion. But how does it actually pull off this amazing trick?
Well, it all comes down to this really simple dance of forces. When you send electricity flowing through a coil of wire, it creates its own little temporary magnet, an electromagnet. Now, if you put that coil near another permanent magnet, they'll start to push and pull on each other. And by cleverly switching the electricity's direction back and forth, you can turn that simple push and pull into a continuous, powerful spin. That right there is the secret sauce behind every single DC motor.
You can think of DC motors as having two main personalities. On one hand, you've got your brushed motors. These are like a reliable old pickup truck. They're simple, cheap to get running, and they just get the job done. But those physical brushes that transfer the power, they wear out, so they need a tune-up now and then. Then you've got brushless motors. These are like a sleek new electric car. They're way more efficient, they last a lot longer, with almost zero maintenance, but yeah, they're a little more complex and more expensive under the hood.
And as you can see here, DC motors are kind of like a team of specialists, right? Each one is designed for a very specific job. Shunt motors are the steady hands, perfect for things like fans and blowers that need a stable, constant speed. Series motors are the absolute heavy lifters, providing that huge initial oomph, that torque, to get massive things like cranes and trains moving from a standstill. And compound motors, well, they're the all-rounders, giving you a great mix of high torque and smooth control for things like elevators.
Okay, so we've got our motor, but how do we actually tell it what to do? How do we get it to go faster or slower on command? Well, the answer lies in the magic of modern electronics. And trust me, it's way smarter than you might think.
Now, you might think, oh, controlling a motor's speed is easy. Just turn down the power, kind of like a dimmer switch for a light bulb. But the tiny computers we use to control these things, microcontrollers, they can't really do that. They think in black and white. It's either fully on or fully off. So to create those shades of gray, we need a much cleverer workaround.
So let me introduce you to the conductor of our little electrical orchestra, the microcontroller. For our example, we're going to be using this super popular one, the Arduino. This little computer chip is the brains of the whole operation. It's capable of sending out perfectly timed signals that will tell the motor exactly how fast to spin. And the secret technique it uses is called pulsed width modulation, or PWM for short, and it is brilliant. Instead of sending a steady stream of power, the Arduino sends a series of super fast on-off pulses. And here's the key. The longer the on time is compared to the off time, that's what we call the duty cycle, the faster the motor spins. It's a really neat digital trick that gives us a smooth, analog-like result.
All right, enough theory. Let's get our hands dirty and actually see how you build a real-life motor circuit. It is time to connect the brains, our Arduino, to the brawn, the actual motor. But hold on. Right away, we hit a snag. The microcontroller is smart, for sure, but it is not strong. It can only put out a tiny little sip of electrical current, maybe 40 milliamps. Our motor, on the other hand, needs a big gulp to get going. If you connect them directly, poof, you will absolutely fry the Arduino's delicate circuits. So we need to bring in some reinforcements.
Meet our two secret weapons for this circuit. First up is the transistor. I want you to think of this as a bouncer at a nightclub. It takes a small, quiet signal from our little microcontroller and uses that signal to open the big main gates, letting a much larger flow of power get to the motor. And second, we have the diode. This is our safety net. When a motor shuts off, it can actually kick back a nasty voltage spike. The diode catches that spike and gives it a safe path to go, protecting our brainy microcontroller from getting zapped.
Okay, let's get building. And don't worry, this is way simpler than it looks. First, we're going to place our key players on the breadboard. Here's our transistor, that's the bouncer, and a small resistor to protect it. And right next to it, our diode, the safety net. We're going to put it right where the motor will eventually connect. All right, step 2. We connect the motor itself, with its 2 wires going on either side of our safety diode. Now for the brawn part of the circuit. This red wire brings in the main power for the motor, coming from a separate 5-volt source. This power is just sitting there, waiting for our transistor to give it the green light.
And now for the final, most crucial link. This yellow wire, this is our communication line. It runs from a special PWM pin on our Arduino directly to the transistor. This is the signal that tells our bouncer when to open and close the gates, pulsing thousands of times a second. And just like that, our circuit is complete. The brain is now safely in control of the brawn.
So, our circuit's built and our motor is spinning away. Fantastic! But what happens when you build this in the real world and nothing happens? Or it starts acting weirdly? We've all been there, right? So let's switch gears from building to fixing and look at some common problems, because even the best engineers spend half their time just troubleshooting.
Okay, problem number 1. Your motor just won't start at all. As you can see on this flowchart, the first step is always to check the simple stuff. Is there a blown fuse? Is the motor's shaft physically stuck on something? If those are fine, it might be an electrical issue. The chart points to an open circuit in the armature. That's just the spinning part with the wire coils, or maybe in the field winding. An open circuit just means there's a break in a wire somewhere inside.
Now, what if you've got the opposite problem? The motor is running way too fast, just out of control. Well, following the chart again, the most likely culprit is that your input voltage is too high. But if that's correct, you might have an internal problem, like a short in those stationary field coils we just talked about. See, if that magnetic field gets weaker, there's less for the motor to push against, and it just speeds up dangerously.
And for our classic brushed motors, this is a big one. You see sparks coming from it. As this chart shows, that's usually a sign of wear and tear. It could mean the commutator, that's the segmented copper ring the brushes touch, is dirty and just needs a good cleaning. Or the brushes themselves are just worn out and need to be replaced. This is why a little maintenance on these pickup truck motors can go a very long way.
You know, we've come a long way. We've gone from a simple dance of magnets all the way to a full working circuit. So now, let's just take a step back from the breadboard for a second and appreciate the truly amazing impact the DC motor has had on a global scale.
So let's just recap what we've covered, because it's a lot. We've demystified the fundamental science behind DC motors, we've seen how to tame them with modern electronics like PWM, and we even walked through building our own safe circuit. And now, we're armed with the basic knowledge to troubleshoot and tackle almost any motor-related challenge that comes our way.
And it is absolutely no exaggeration to say this technology changed the world. Think about it. Before the DC motor, a factory had one giant steam engine and this complex, dangerous web of belts and pulleys to power every single machine. The DC motor let power be delivered directly and efficiently to individual machines. This is what made the modern assembly line, like the one Henry Ford made famous, even possible. That legacy continues to drive innovation today in everything from electric vehicles to robots that explore other planets.
The DC motor is such a simple but an incredibly powerful tool. It's one of the fundamental building blocks of our modern world. Now that you know how it works, how to control it, and how to fix it, what will you build with it? The possibilities are literally endless.